Welcome to CIV4SD3 Week 3 lectures. Um, we are going to discuss the design of singly reinforced concrete beams using the Australian standard AS3600. The structure of the lecture is divided into two parts. First 1 hour, we are going to talk about the theory. uh, Dr. Haider Alabadi will going to take us from theory of the lectures, which is approximately 1 hour, about one o'clock, and from 1 to 2, I will demonstrate the one examples that's given in our lecture notes, and that examples that will be the part of the second half of the lectures. So as I mentioned, this week we are going to design the reinforced concrete beams. When we deliver the lectures, when we take you through the theory, and when we take you through the examples, I encourage you to keep the AS3600 open with you. So when in the lectures they referring any clause or any theory or any equations, I encourage you to open the standards and see where they are located in any particular location or particular page. So just make yourself familiar more and more with the Australian standard AS3600 along with the lectures that we are delivering. Of course, we're going to show you on the screen where in the standard the equations that we are taking, which tables we are using. Of course, there will be more informations there. There is no any skipping. We will let you take you through all the details, but to be have more useful and more engaging for you, we encourage you to keep your Australian standard opens on your desk. If possible, if you use pen and papers with us, and follow the instructions, take the equations, plug the values from the standards, and use these information rather than just a listening. It would not help you if you are listening us for 100 times. It will be more useful if you are performing that examples by yourself. So I think in about 3 minutes, um, let's everyone get in, and 12:05 Header will going to take us through the first half of the lectures. Tomorrow we have a workshop, face-to-face workshop um, in Bandura and Bendigo. We will also run the online workshops. We encourage students to utilize the face-to-face workshop if possible. That will be more engaging. You can ask questions if you are facing any issue about the subjects or any technical questions that you may arise. We encourage students to just come on campus and use our facilities, the things there, so we can provide you more supports if you are in the face-to-face workshop. Of course, in online also we will answer all the questions as we have face-to-face, but um, but we cannot replace the whole face-to-face experience in an online mode. We were trying, but just to be on the side that face-to-face are more engaging and more learning intensives, that we have placed tomorrow. So I think in 2 minutes times we will take you through the lectures in 1 minute time. Thanks everyone for joining early. Thanks, Ada.
Thank you, Vipul. Okay, 12:05. Good afternoon, students. Which you're having a good start with week 3. And as promised, so from this week, we will get you into the process of finding the strength for reinforced concrete beams, which is one of the key things designers need to figure out. And you know, the story is from structures 1 plus other skills, you're going to find how much bending action, shear action, which are the starred one, the factored one, are imposed onto our concrete, reinforced concrete sections. And on the other side, we want to find the strength they can take and whether they can take it and what else we can do. So today we will start talking about the design, right? To have a gentle start and a simple start, we're going to only look to cases where the sections are singly reinforced. What does that mean? The reinforcement is located on the tension side only of the beam, whether top and bottom. So some people will think it's always bottom. That's what we're going to be sketching to you, because we're assuming the beam is like this. The loading is on the top of the beam, and the bending moment diagram is like this. So you know, when we have the bending bent like that, the tension is at the bottom. That's why the steel is at the bottom. However, if we got a beam which is cantilevered out of something like this, yeah, sorry for the color, so I'll change it to purple. Yeah, it's cantilevered like this. Now, you know, here we got negative bending. So if I come back to my section and I want to still design it as singly reinforced, the bars should be at the top and no reinforcement at the bottom. Yeah, because the tension is at the top. So just know, singly reinforced, the bars can be at the bottom or at the top, one side. But next week, we're going to talk about doubly reinforced, because we have the reinforcement spotted at both directions. Sorry, both sides. So week 3, as we just briefed you, it is about singly reinforced. Why we don't jump straight away to here is just to gently build the theory in your minds. So this guy here, this is the beam. I can see this is a precast concrete beam, and it is one of the things you will be able to figure out, but we're assuming it's singly reinforced. Maybe someone will say, I think it's doubly reinforced. Yeah, maybe, but this is one of the beam structures we're going to looking at. So this is, again, the sections we're going to be dealing with. We're going to take you through. You need to build a correct understanding for these diagrams. One of them is called stress diagram, one of the others called strain. There's a really story behind it. Try to carefully understand it from the lectures or from the worked examples carefully, so you build the correct understanding and things won't go wrong. Okay. So 3 sections I will take you through, and then a very decent example which should recap and should apply all the theories. Introduction, load. We got introduction now to go through. Then we're going to talk about load deflection responses, just so you understand how the formulas are reflected in the real world, and what does it mean for the designers to cope with those correct formulas and how it's going to be reflected in the design. Then we're going to get to the point of the equations. Now, just to say it from now, while we're going to teach you the singly reinforced, which I was saying it's a very simple start, we're going to show you how to find the strength by using 2 methods. Number 1, we're going to show you how to use first principles. So put it this way, first principles means you're going to be finding the formulas from scratch by plotting the diagrams, the stress and strain diagrams. You will understand more later. That was the first method. The second method is just use a formula. And that formula, basically, it was generated from first principles. However, someone will say then, why you don't ask us to use the formula and full stop? This won't be enough for you to build correct understanding for next week, the doubly reinforced, the doubly reinforced section. When we have top and bottom, it's going to be very difficult for you to use the prepared formula and find a design for top and bottom reinforcement. You need to know the first principles. So by the end of today and the examples, and also tomorrow's example, you should be on top of managing to design a beam by using either first principles, by using the stress and strain diagrams, or the more simpler, it's not simpler, it's just faster method by using a formula. And you need, in the final exam or test, we may ask you one of them. We may tell you use first principles, or we may ask you to use we may say nothing, then it's up to you. So just put this in mind before we get into the equation. So before we're getting into the formulas, we cannot just jump to the, you're going to be professional engineers where you need to know the theory and link it with formula and then application. So we have to go through some general introductions and discussions. The thing, designing reinforced concrete sections, and what we're going to be talking about today, we're going to talking about designing beams. And we're going to talk about beams from now until just a little bit after the middle of the semester. Then we're going to talk about slabs, then columns. So from week 3 today, I think almost to week 6 or 7, we will be still talking about beams, right? Because next week it's going to be the doubly reinforced. Then the week after we're going to talk about shear. Then the week after we're going to talk about deflection. Then we're going to have some decent examples. So say we're going to talk about beams for a while. And then we're going to change the component and talk about slabs. Then we end it with columns, and that would be enough. So, and you all know what beam is. The beam is the horizontally spanning element which takes loads in the transverse direction. Transverse direction, it is the direction perpendicular to its longitudinal axis. So if I look this way, if I look this way to my beam, then this is, let me change it to a pen. This is going to be the span, and the axis of the span is going through here, right? And the load is actually perpendicular to the axis of the span. So usually we call these loads transverse loads. Okay, that's what I mean, and that's the beam. The beam gonna end up being under deflection or flexure. To make it under deflection or flexure, it should be caused by transverse loads, which is actually perpendicular to the axis, which is the span axis. So the second point we have here was about, yes, it is those beams typically are supported on another beam, or it can be supported on the column. We talked about this last year, if you remember, when we talked about steel beams. It's just the same thing. Now, reinforced concrete beams can be cast in situ. So what does that mean? They can be poured on site, and they can be poured together with the slabs, like this beam, this edge beam. Typically, they don't pour the beam and make a construction joint here and then pour the slab. They will pour the slab and the beam together. We have a picture in the following slide to understand the same thing here. We have, this is a beam. Remember, this may be a slab running along. We have a picture just behind here. You see, this is the beam and this is the slab, and they're pouring them. They're going to pour them together. They're going to box it out. They're going to box everything together, right? And they're going to pour the slab and the beam all monolithically together. And that's really what we're trying to say here. Sometimes when we need to do precast, we're going to do this. This is for reasons like it's very high and they don't want to prop it. They can't prop it on site. Just going to cost a lot, and there's no point. That's where builders going to think about the precast sections. So they're going to build the beam in the factory. Usually I would say this is pre-stressed, but this is not our topic. So it is reinforced concrete section, whether RC or PT, but they're gonna build it in the factory, then just crane it and put it on site. That's not in situ. It's not poured on site. It's poured off site. So and that's example I was showing you, the off site, the precast section. It cannot be poured together with the slab. Obviously, the slab gonna come and either poured on top of it, or it's gonna be just also precasted slab and placed on top of it. All right, so the beams are typically laid, or they are framed in the horizontal direction, and they have a cross section which is much more smaller than the length. Usually the span can go up to 7 meters, like RC structures, normal reinforced concrete, not post-tension. They can go up to 7 meters easily with the normal conventional level of reinforcement. I would say 7 meters long, but remember that beam will be only, say, 600 deep in millimeters, and it would be about, so say 600 millimeters deep, and I would say about, how much we say, half a meter wide, or maybe 400, half a meter still, say 400 millimeters wide, but it will be spanning for about 7 meters, which is 7,000 millimeters long. So that was the point number 4 it's talking about. Usually they are placed in the horizontal, like in horizontal direction. They're spanning about 7 meters or so, and the cross-sectional dimensions are really small. But just to let you know, still the beams can be sloped, like what we see in ramps. You know, in the car parks, you've got ramps. They are sloping. The beams can still be sloped there. They don't need to be horizontal. They can also be sloped. But remember, when they are sloped, the designers have to consider some sort of axial load as well. Because if you got a beam like this, it will be connected to a footing. It's like a ramp, like a car park. Got the car here. Yeah, so this may be a beam, and there is a beam on the other side and a slab in between. So I would say this section, yes, it's going to be mostly under bending. We design it as a beam, but at the same time, there is some axial load because it is not it's not only horizontal, it's also get compression due to the load from the vehicle or the own weight of the slab. So this is just for your information. In this subject, we're only going to design horizontal beams. The last point here is talking to you about the shape of the beam. Ideally, and what we're going to be mostly doing in this subject, we're going to work with rectangular sections, which will give you all the knowledge you need and let you go from there. Now, however, usually beams and when as we said, the beam and the slabs, they are poured together, then they will effectively form an L shape for the edge beam, or they form a T shape for the internal beam. What does that mean? If I go back to this picture, this beam, it won't be an economical design if you only get to design it as rectangular like this, right? It is actually a T section. So it is actually a section like this, a T. Now, someone may ask me a question. He will say, how wide is the T? Is the T is like the flange of the T, the top flange of the T section, how wide it is? Can we take it as wide as we go from half slab to the half slab? No, the standards will tell you what's the maximum width. It's about it should be about 1.5 meters or so maximum. We cannot take the full width of the slab, and we will talk about this in a special section, not this week, I think later on. However, just to let you know, our questions We will not ask you to design a T section. It's not difficult. It just takes longer and longer, and we will mention that to you when we get to that topic over the weeks. For now, what we're trying to say, the concrete sections that we're going to study together are going to be rectangular shapes. However, in real applications, they can be formed as H beam, L shape, or T shape. There's also other shapes like hollow for bridges. They use hollow boxes, but this is, again, the theory will stay same. You're just going to play with some different geometries and different inertia values, and you can take it from there. You either can do it by hand, but you can use softwares to let you do the calculation. So these were just some real concrete structures from Bendigo campus. Yeah, the concrete sections are very clear there. You can see this is the edge beam. So if I cut a section through here, the concrete beam will be something like this and connected obviously to the slab because they poured together. Now, when I'm going to design this edge beam, design it effectively, I would also use some of the slab because it's there whether you like it or not. So I would design for this section. As I said, the width of the flange is determined by a standard formula, which depends on how much stress we're getting into the slab. And it's typically about, say, 1.5, 1.2 meters. So we're talking here, this is about 0.4. I would say the beam width here is about 0.4, 400 millimeters. Okay. If you have any questions, just unmute and ask, because maybe if someone asks here, I can't see the question, but if you have a question, you want me to stop somewhere, just let me know. So we're done with the introduction. Now let's talk about load deflection. Again, we will start, you're going to start seeing equations here. So I'm going to a little bit speed up with section 2, and then we're going to have a decent example. So load deflection, what we're going to talk about here is, it's really critical and important to build a good understanding about. We need to know what the concrete, reinforced concrete beam is suffering from while we're loading him from the day it was created or born or poured. Yeah. So there is an experience that will be there will be behaviors. The better way to say it, the beam will go under behaviors while they experience loads on top of them. If you remember last year when we talked to you about designing steel beams, we said to you, to understand how we design them, we have to imagine what failure modes the steel beam will suffer from. And we talked about the yielding failure, we talked about the buckling of the flanges, the buckling of the web of the beam. You remember these 7-6 cases. Okay, so that's if you don't, just don't worry about it. Same thing with reinforced concrete. We have to understand what they're going to experience over the loading time from the first time we actually built the concrete. So just imagine with me, this is a simply supported reinforced concrete section, and say in day one you're going to be as we all know, when we build reinforced concrete section, we're going to have it sitting on the form, okay, the formwork. So it's carrying nothing. From the day we pour the concrete, it's gonna get hardened, and still it's not really carrying nothing because it's still sitting on the formwork, right? Now, from the day we remove and strip the formwork, that's the first hit of load it will experience. What does it experience is what's shown in 1, 2, 3. And depends again on the level of load it is under. You need to, okay, what we're seeing in this graph, we're seeing a vertical axis, which is the load, and a horizontal axis, which is a deflection. So as I said, by the time the fresh concrete or the new slab is sitting on the formwork, it's carrying nothing. We are here. No load, no deflection, obviously. Now, by the time we strip away the the formwork, what it will carry its own weight, right? And I can tell you, typically, by the time we take the own weight, we're going to be somewhere here. By the time the slab carries its own weight, even though nothing live load, because obviously nobody will be standing on a slab by the time you strip it off. Which will be within, yeah, maybe construction people will be there, that's fine. But I'm talking about the load and eventually the bending action. You know, if we have load causes bending, like for you know, M is equal to, what was the formula? WL squared over 8. You had it from mechanics of solids. So if you have load, this is the span over 8, square the span, you will have the bending. When I say bending, it means also load, right? So what we're trying to say here, by the time you take away the formwork from under a fresh slab, it will be under somewhere here. Now, I didn't mention an important point here. You need to understand that the concrete have two main phases in terms of cracking. Number one, uncracked phase, then cracked phase. The uncracked phase, it is from the day the slab is born, or you actually pour the slab, until you load it with what we call it MCR. MCR is the cracking moment. It's the moment when the cracks will happen. Now, someone will say, but you said we don't want cracks. And you said we're going to be here. And we have the limit up to there for the maximum, you know, capacity of the beam, right? Remember the cracks we're talking about, they are micro cracks. You don't see them. And we want those cracks to happen. Because when the cracks happen, that means the steel will start working at the tension side and the system will start working. So if I make a quick rectangular section here, where I've got Rio at the bottom, where the tension is, remember it's simply supported, so the tension is at the bottom. And there is the neutral axis. We talked about this in mechanics of solids. As we said, the area below the neutral axis gonna actually crack at this level. So in within those microseconds, when you are removing and stripping the formwork, like from no load to cracking load, the beam the loading and the M crack will start from 0 to M crack. Now what's happening there? We're opening very micro cracks that you don't see. And by the time the crack starts, so we are here at this level. Okay, so what I'm trying to say, there is an imaginary uncracked phase a concrete beam gonna be under. Now, yes, I can say if you designed a very, very deep concrete and you didn't crack it, yes, you may be staying at uncracked, but this is not feasible. It won't happen, because that means your beam may need to be 2 meters deep, not 600 deep. And nobody will do this. There's no 2 meters deep. The floor is 2 meters something. So nobody will design a beam 2 meters deep, right? So what I'm trying to say is, by the time we apply load on the beam, we're actually gonna crack it. And when we say cracking it, we're talking about micro cracks you don't see by your eyes. When the cracks happens, then the steel gonna get into business and start doing its intended job. Above neutral axis, the concrete is still active. No cracks here, no cracks. So when you hear and say us talking about uncracked and cracked, we're not talking about the full section is cracked, or those excessive cracks that we're gonna prevent by the steel anyway. We're talking about those micro cracks which are required, and we need to reach in order to get the system to get engaged into the system, and things will work correctly. So stage number 1, again, it is the cracked stage where the micro cracks will happen, and then your beam will be typically working within this phase, and depends on the load. You know, if we have if there is no load on the slab, we're going to be somewhere here. If we have more loads, we're going to go higher, but the maximum we're going to get to is M ultimate, and this is what you're going to design by the end of this week. You will be able to determine to us phi MUO. This is our aim. We're trying to find the maximum ultimate bending capacity for a beam. We're going to show you the formula, full stop. This was the aim of this week's topic, and it's for singly reinforced section, remember. Now, so the first thing you need to understand is the beam going to suffer from cracking, which is okay. It's only going to crack on the tension side, and that's why we want it to happen, so the steel going to get into business. Then the other failure it's going to face is the yielding failure. The steel going to reach its maximum capacity, where the steel going to reach its maximum capacity. And yes, we designed for this as well. So I can tell you, yes, we designed for this. So all our design is going to be based on letting the steel reach yield, which we said last week, and last 2 weeks is 500 MPa. This is the FY. We need to design for the yield steel, which is all good. Now, from this point to point number 3, no more strength you will get. You will gain no more strength. However, you're going to be capped by a capacity called crushing of concrete, and that will be the killing failure, where the top side of your concrete going to get crushed. And in week 1, we start talking to you about this. Remember when I said to you the concrete cannot be strained more than 0.003. Otherwise, it's going to get crushed somewhere here. And this is our limiting value for the capacity, right? So in summary, this curve just shows you a quick summary about what are the 3 key points or milestones. And at these points, there are values that we will take into calculations as we go. There is a cracking moment. This cracking moment helps us to determine the minimum reinforcement we need, or the minimum strength we need, because we need to make sure the system is switched on in terms of the steel is doing something, right? We cannot design for sections that are not cracked, because it means we may have, there's something wrong, and effectively nobody would design for the end crack, for non-cracking sections, because it's going to be very, very, very deep beam. So then the second milestone is we need to design and consider the steel is yielded. So we have 500 MPa already. We have the steel tensioned at 500 MPa. And there's another phase we need to consider. We need to block the strain of concrete to not exceed the 0.003 figure we talked about, because the concrete gonna get crushed. I'm talking here about the compressed side of the beam. Now, these kind of things will get clearer and clearer as we start playing with equations and numbers, but it's good to really understand the theory in the right way. This image here, or this slide, is kind of talking about what I mentioned in a different way. So this is the same curve, right? And now here we're trying to explain what's happening to the face of the section. This is just a cut. So what we did, we had a cut here, right? And imagine we have a rectangular beam with reinforcement on the tension side. And we're trying here to explain to you what's happening to the face of concrete, or to that section, as we load it over the 3 phases or stage. Okay. Now, the first, that's, I said to you, we're going to ask you to design things based on first principles. And when I mentioned this word, I mentioned first principles means you're going to use stress and strain diagrams. These are the stress and strain diagram. So just in case you don't know what I mean, the strain diagram, remember here we're showing it in 2D, but in reality is a 3D, because the strain is, we're going to have really a picture which we used in mechanics of solids, just to help me here, this one, it's like this. So the 2D we talking about before, in reality they are 3D, just bear this in mind. And if I go back to where I was, so back to this one, you had here as the first column here represents the strain, the second column represents stress, and here we're just going to focus on the 3 phases. All right, just again to build a correct understanding for those milestones I mentioned here. So what's really happening with phase number 1 It is the point where, as we said, the concrete will reach its maximum tensile capacity to take shear. We talked about this in week 1, and I said to you this character here, which is F prime CT dot F, and we said this is 60% of root square FC prime. And we said when the beam is under bending, there's gonna be a formula that we were gonna be using to determine what's the maximum flexure tension capacity for the beam to take, and it was here. And in reality, what does that mean? If we exceed these, if this, remember this was the stress diagram, if the stress here exceeded what the concrete can take, we said it's about 3 or 4 MPa, then the cracks will start, which is okay. We want it to start. So that was phase 1. That's really what's happening at phase 1. And that's where we try to say here at, this is the initiation of the cracks in concrete under tension. Check, all good. Then what's happening at phase number 2, which we're going to be designing for. At this phase, you see what we, don't worry about strains now. Let's talk about stresses. We're showing no stresses. Can someone quickly tell me why we're showing no stress? We're showing no stresses, like there's no curve here.
The concrete is cracked, then it has no ability to...
Excellent, that's it, because concrete is cracked. The gray concrete is gone, but who's with us playing the game is Mr. Steel. And that's why, you're gonna see this from first principles. We can always plot these things, right? So steel is under tension, and how to find its value, the tension, simply what we did in mechanics of solids, multiply area by stress. The area is the area of steel. The stress is the 500 MPa. That's it. Now, as you're going to see in our design, sometimes we will ask you for area steel, so you just work it out differently. You're going to see there is also, what about the compression? It's here. We're going to have a C component. Now, there is something we're going to teach you about, because you're going to see this shape is a bit odd, the shape of the compression stress on the gray concrete, because we know that the concrete is good at compression. So we still have stress here, but the shape is odd, it's non-linear. Mr. Standard will simplify this in a rectangular shape, and just we're going to touch on this in the coming slides, so don't worry about it. Now, what about the strain curve here? It's just telling us that the steel is at yield, and these are one of the checks we're going to do with the first principles. Eta SY means the strain of the steel, Y means yield. Now, eta SY is equal to 500, which is the yield strength of concrete, over E, which is 200,000. Because we know strain is equal to stress over Young's modulus, mechanics of solids. Okay, we will touch on this again, but I just want here to fill the gaps. So what I'm trying to say, at this phase, the steel is at yield, right? And that's what we want. We want the steel to yield, to let it do the job it's intended to do. To check the steel is at yield, we have to make sure the strain value here, right, is 0.0025. From where this number? It simply came from dividing 500 MPa, which is the yield strength of the steel bars, over the EVA, the Young's modulus of the steel. If you divide these two numbers, will give you. So we're going to do this in our hand calculations. You're going to see that. So you're going to practice it slowly. Just want to finish on time, so you have enough time to practice the examples. So the last phase, that's the killing point. And that's, again, we're going to use this strain. This is very important diagram here. Whenever we're going to plot, whenever we're going to use first principles to plot the strain diagram, we're going to cap it with 0.03003, right? Because in week 1 and last 2 weeks, we said to you, the concrete will get crushed if it's strained more than 0.003, which is the 0.3%. So that's why here it's sitting on our curves, the strain curve. It's more critical. You see, this did not change. It did not change. The stress diagram didn't change. Why? Because as I said to you, it's just gonna stay same. However, when your beam gonna fail, and we're gonna see those big cracks, the failure cracks, it is if we exceed this condition. And we're gonna see, so just make sure you know about this strain diagram. So basically, those three phases are phases are critical ones to theoretically understand, and that will help you to develop a smooth run through your calculations. Now, what's this curve is telling us? It's just a message telling you that we need to design our reinforced concrete sections to be with adequate ductility. We want it to flex, to give us warning, right? And with experience from standards, they're always going to tell you the good ductility level in terms of steel ratio is defined when the steel ratio is actually just about this figure here, because you see it's giving us warning. We cannot design, because someone will say, wow, we have very high capacity here for the concrete. It can take a lot of bending. But remember, if accidents happen and people overload a slab or a beam, you're just going to break it without warning. It's going to break and goodbye. But with these figures, you have some sort of warning. The slab going to sag. It's going to give us cracks and it's going to warn you. So as per the standards, one of the key ways to make sure that we have enough ductility, we have a couple of ways. One of them is finding the steel ratio. What's the steel ratio? Is the ratio between the quantity of steel, these guys, we can find it from Rio data, divided over B over area. What's this area? Just don't get confused. The small d is the effective depth of the steel. So it's from the compressed side of the beam to the center of the bars, not the full depth. Okay, usually our effective depth, or the small d, it is from the compressed side, the top of the. Now I don't want to say always top. As I said, if we have a cantilever, the story going to change. We're going to have bar this way. So our small d going to be from the center of the bar to this side. So I don't want to say from the top. I'm saying from the compressed side, from the upper fiber of the compressed side. Again, I said upper. I should say the far end of the compressed side towards the center of the tension bars. That's the D, small d. Yeah. And multiply this by the width of the beam. This will give you the area of the concrete. And area steel, as I said, it is the area of simply the steel, and you either going to be asked to find it, or you're going to be asked to use it to find the M ultimate. Now, yeah, so this slide's really just summarize what I said to you already. By standards, we need to make sure the steel ratio does not go more than this figure to give us the warning. As I said here, it's giving us the warning, and yeah, I think, and also it's really to help if we got indeterminate structures. The structure, if there is like talking about car parks and one of the columns were hit by a car, and the columns get damaged partially or whatever, then the slab can do something, can work non-linearly and deflect without the whole thing getting collapsed down. Okay, which is in the end of the day enhances robustness. Okay, so by regulations, we cannot have very, very high steel ratio. Right, so we've got about 15 minutes or so. And here I'm gonna scan you through the equations, which, as we said, the goal is here to find the MUO. Okay, that's going to give you the ultimate bending capacity of a reinforced concrete section, which was this value here. And remember, sometimes, as you're going to see, you're going to have two types of questions. We're going to do one of them today, and tomorrow in the workshops we're going to do the other. Sometimes we may ask you to find the area steel instead of finding. So we give you this to find that. We give you, and I will really mention things where people do a killing mistakes in their final exam. But we'll talk about this later. For now, just again about the steps they follow Now let's talk about the equations and capacity. So as we said to you, this was just an experiment showing you how the beam gonna give up and kill itself as it's overloaded. So you say we want to, these are the strength failure cracks, the micro cracks, you don't see them, which we, the other ones when we reach M cracked or the loading crack. This is when does this happen? It happens when we reach the 0.3, the strain. Okay, so obviously we want to design our concrete where these failures will not happen. This is again is just a recapping. Just before I jump into the stresses that we have for reinforced concrete, I just want to refresh your memories about mechanics of solids, where we had homogeneous and isotropic material. Remember in mechanics of solids, when things were simple, we said you have a material, whether steel or X material, and it's homogeneous. And it is isotropic. Isotropic means that its properties in whatever direction behaves in the same manner. What's happening there if you've got a simply supported beam, or let's start from here, you've got just a beam, it's under load, its line diagram looks like this. And when it's under load, the bending can be calculated from simple analysis with WL squared over 8. Then if we focus on a section like here, we're going to look at this diagram here. We're going to have the stresses evenly distributed, correct? So what I mean, the neutral axis will be in the center because we had this homogeneous symmetrical section. It was just a rectangle. So you can straight away say the neutral axis is in the center. Now in RC, one of the strange things or new things, the neutral axes were not likely or definitely not be always in the middle. Why? Because here we have a composite section between, and we have a cracked section, right, where things gonna change. The neutral axis will be moving upwards. Okay, so that's, but here again, we just want you to remember from plotting the stresses, we can, before, we used to quickly work out the C component and the T components in mechanics of solids. The C component was just finding this area, this triangular area, which is equal to the what? T, the tension area. And you just multiply the compressive stress by half of the beam depth, and then you're going to multiply by the width of by B, the width of the section. That will give you the CC. And if you want to find the moment, the capacity of the section, you just multiply one of those, C, by the lever arm. That was before. And again, that's all described here. So again, this section was a symmetrical section, but here in RC, in this subject, we will have things different. However, the good thing is standard came in and made things a bit simpler for us. And we just need to follow formulas to shape up the correct, I will put it here. So this was the non-real imaginary stress diagram that you can assume on a homogeneous isotropic section. In reinforced concrete, our stress diagram will look something like this. The neutral axis will be somewhere here. And as we said, we have here, yet we put T for U, but in reality, you can also say there are stresses on the bar. Yeah, we got the stress only on the reinforced bar, and the compression will be a simplified rectangular shape, which was introduced to us by the standard. So this is what we have in RC, and this is what you would see from mechanics of solids in a, as I said, isotropic or homogeneous section, something like fully rectangular steel sections, but nobody will design a full rectangular steel section. It's just too expensive to do so. And we kind of used these principles in last year when we talked about steel. Okay, so from here, just understand your typical stress diagram will look something like this. Now, before we jump into those diagrams, we're just going to touch on the limit state design method. Remember, we introduced you to this method last year, and we said when we design any structural element, we have to design it for strength, which is making sure it will not break. We design it for serviceability, which means a couple of things, including sagging. We will study this in this subject. And also fire, we studied this last week. Durability, we studied this last week, which was all about looking into tables, right? Now, the limit state design method, what does it say? Make sure your actions are typically less than the capacity it can take. You are good at this. You already passed and had A's or B's, and you know how to find actions now. Okay. Although for concrete, we will let you find different ways. There is section 6 in your standards will let you know how to find actions with formulas, not by softwares. So we will also introduce you to this. And that's what we saying here. Okay, now what about this? This is what we're gonna start doing this week. You're gonna find the capacity. Now the capacity here can mean many things. Yeah, it can mean bending, shear, torsion, any other actions the beam can experience. But what we're doing this week is we're going to be talking about bending. So we're talking about bending capacity. Then to make sure we include safety factors, we're going to multiply the bending capacity by a phi. And that's where we can then make the check and things will be okay. And this is what I was saying, a star is something you are good at it and you know how to find actions. With serviceability, as we said, it covers all these things. You're going to do this about week 6. You will also do this in our designs. You did this already, and this is water tightness, which is as it's just up to the add mixtures. Now, some assumptions before I show you those formulas, and again, they're going to be carefully going through in the examples. There are assumptions we always take into consideration. Number one, you know the strain diagrams you're going to keep plotting, and we showed you we always assume they are linear. They are linear, and that's acceptable assumption because the concrete beam, it's bonded with the reinforced bars. So they are moving together. Someone will say, didn't we say this is cracked? Well, I know it's cracked, but it didn't go away. And I know it does not take stress. However, in terms of straining and displacement, it will move. So the concrete is there in terms of strain, but it is not there in terms of stress because concrete cannot take tension, but it is there in terms of strain. And the main thing we are talking about here is the steel. And why the steel is moving with the concrete? Because there is those the threads around the bars. There is bond between them. That's assumption number one. Assumption number two, the steel the steel stress strain diagram will be represented as shown with this shape here, right? Because you know when you test a steel bar, it's gonna behave like that, like the dash line. Then the standard said no, we don't need to take this extra strain hardening, just neglect it and always model it like this. What does this mean? It means that typically the ES, the Young's modulus of steel calculated from this slope, it is 200,000. Always take it this way. The F yield for bars we said is 500. If you divide 500 over this figure, it will give us the strain, which as I said to you, it's 0.5%. So let me go through this before we start the example. And this is the end of in these slides. We're just going to talk about this stress on the compressive stress on the block of concrete. As we said, we're not showing here what's happening below the neutral axis because it's cracked. And we know the steel bar is going to take T and the tension stress. So it's very easy. Just multiply the area of steel by the 500 MPa, full stop. You're going to get the T value. Now, what's happening at the top is complicated. If you go through the phases, the steel, while we start loading the concrete, the stress compressive distribution going to look like this at the start. But as you load it, it will get more and more non-linear, get more and more stress. Now, even at the top, it's going to get constant. Now, this is the actual stress profile on the concrete compressed side. As you can see, it's complicated, it's difficult to model. So what they did, the standards, they decided to come up with a defined shape, rectangular, that's what they call a Whitney stress block or rectangular stress block. And all the standards use something like this. And now what they did, I think effectively, you're going to see this hatched area is equal to this hatched area. And these parameters will help. There is a parameter for a horizontal direction, a parameter for the vertical direction, and these parameters will help us to define the actual shape or the size of the rectangular block, and also the location of the C. Why? Because the standards will define this depth, and when you know this depth, you will determine the center location of that depth will tell you where is the C located. Okay, so I can tell you there is 6, 7, 8 parameters. You will be going through them in the examples. Take this gentle time to really do things, you know, tonight. So tomorrow you're going to get into the other example. And what I would tell you here as well, I'm sure you will, with the examples, you're going to be slowly defined and know all these details. But in summary, like a big picture of it, we here defining a rectangular block. Remember, I'm saying block, not it's a 3D block. So because here we still have a width. I think there's an image which shows us the 3D, not sure. So it's a block pushing the concrete side at the compressed side. All right, and you're going to find C, we're going to multiply this side, which was alpha to FC, by this side, which is, again, someone will ask me, what are those? They are from the standards, and you're going to go through them slowly. So just wait for that. Then after I multiply this side by that side, remember it's a volume, I'm going to multiply it by the width B of the section, which is here, right? So in other words, we are trying to find the C component, which represents the compressed force on the concrete side, and it's coming from these sides which are defined by the standards. Why they are defined by the standards? Because they want to simplify the shape. We will not use this, just to simplify it to you. We're going to use this shape always. Okay, so now I did tell you these parameters from the standards. Here they are. This came from the standards. I don't need to say more than this because you will see these things. So you remember here we're getting to what the mechanics of solids was telling us. By the time you define C, and we already know T simply is just the stress on the bars. Just find it by area of the bars multiplied by 500 MPa, full stop. Then you will end up with an equation, or we're going to use statics here. We're going to leave as the structural design 2, we're going to go back to mechanics of solids. We're going to apply statics, equate C with T, and it will help us with some formulas. You see, this is the aim. This was the goal, yeah? That was the goal. We want to find M, and then we multiply it by phi, and here we go. The aim was to find the ultimate capacity of the section. Okay, there are some things which we will talk about slowly over the example, like this is important parameter Ku. I know I didn't talk about it in depth, but I will leave it to the example and we can discuss it more and more over the workshops tomorrow. Now, I've got maybe quick thing to mention to you. So there are some minimum requirements that we need to achieve after we find our M capacity. There are minimum requirements to achieve, which are defined by the standards, and we're going to see them. Now, I think there is also some limitations about the Ku. Remember when I said to you, we need to make sure the beams are ductile enough. And one of the ways to do this is to look to the steel ratio, the rho, which was equal to area of steel over the area of the concrete. We have another game to do for this check as well, to do with the Ku, and we will talk to you about this, okay? One thing I want to mention, we will visit these things. I know this is the start of next week lecture, so I'm not talking about it now. There's a story behind this, but this will not conflict with what you need to learn this week. I will talk to you about this in week 4 next week, and I don't think it's going to conflict with what we're doing this week or the examples we're doing. These are the minimum strength requirement, which as we do the design and we finish the design and we found our MU as per, you know, the first principles I showed you, etc. We have to do a few checks, and some of them are here. One of them, you need to make sure your strength is minimum 20% more than the cracked bending. Okay, this is from the standard. You don't need to memorize nothing, but just make sure this step is done. Otherwise, you're going to lose marks. So what we have to do, we need to make sure the minimum strength you ended up calculating, it's not less than this figure. Why are we doing this? We need to make sure the section is cracked. Didn't we say we need to do these micro cracks for the system to switch on and work? So this is why we're doing this check. Okay, and which is also ended up with minimum reinforcement. All right, I think this really just give you quick definitions, and I will give it to Vipul. No, thanks, Vipul.
Thank you, Heather, for taking this theory. Probably now the theory is covered extensively, so now we're going to take you through the examples that will be just backing up the theory that you just witnessed, and that examples that I will going to share with you now in a minute. If you have any questions in between, just unmute or put in the chat. If any values that does not make sense or any burning questions that comes along, don't hesitate to just put in the chat or unmute yourself, and we can have a good discussion. Hopefully you can hear me. You can see my screen. I will turn off my camera because I need to switch this Surface Pro on the table, so you will just see the screen now. So let me read through these examples. You can see these examples on your LMS as well. Now here in these examples that you are seeing, that examples that you're seeing, example number 1, analysis of known sections. Now there are two kinds of examples that you will come across in the beam. One is the analysis. What does it mean, analysis? Analysis meaning that you will given the B value, like what is the width, and you will be given what is the depth. The cross section is known to you, so cross section size is given, right? Meaning that you need to calculate 5 MUO, the capacity of the bending capacity of the given sections. Another examples you may come across is a design, where they give you the design bending moment, M star, and then you estimate the cross section size. There is another kind, that how much B and D is required to carry this M star value, right? So there are two kinds. So this first kind that you have, that we're going to analyzing, and in the first there is another type as well. You might need to estimate the reinforcement requirements. That might be the questions as well, or this might be the questions. Or in the second part, again you need to estimate the reinforcement. But this is the overall. So determining the moment capacity, which is basically 5 MUO, using the first principles of 600 millimeters. The depth is 600 millimeters given in the figure. That is capital D. Let me list them here. Capital D is equal to 600 millimeters. Let's write given data. Let me put the black color. D equal to given. Now another one is given to us, B. So B equal to 300 millimeters. And singly reinforced that we will probably next week when we explain the doubly reinforced, you will be consider how you're going to distinguish between singly reinforced and doubly reinforced. Rectangular sections, concrete compressive strength given to us 25 megapascals. The AST given 3. So let's list that. FC dash is equal to 25 megapascal given to us. Then you have AST, area of the steel reinforcement, given 3 and 24. So let me explain you what is 3 and 24 meaning. 3, first number is number of bars, meaning that you can see here 1, 2 and 3. There are 3 bars. That's what the designation of this. N stands for the normal ductility class. Normal ductility. That is the class of your reinforcement. If I take you, I think this one is not working. Let me fix up this. Give me a minute. I'm just turning it on this software again to open up this. Yep, I can see now. So here, I think the ductility that you want to see is in somewhere here in the section 3. I hope you can see, as I mentioned. Yep, you cannot see it. Let me turn off the lamp. Yep, so probably this is better. Here you go. There is a clause 3.2.1 ductility of reinforcement characterized by low ductility, normal ductility class given in the 3.2.1. So that is just a normal ductility class that's written over there. Now 24 stand for the diameter of the 24 millimeter is the diameter of reinforcement. Right, so that's the meaning of these 3 and 24 bar. 40 millimeter cover and R10 fitments. So 40 millimeter cover to given to us, and R10 fitments. Right, so that's all good. Let me go through it. One of the examples, or let me take you through this. I will share you the screen in a minute. I just need to get the photographs that will help me to explain you the theory. Concrete. So let me get the photograph. So here is the one photograph. Here is another photograph that I want to use. Yep, there you go. I'm just going to share with you the screen in a minute. And that is another photograph that I want to use. Okay. And then yep, just sharing with you in a minute. Okay, so that's all good. And the last photographs that I wanted is this. All right. Now let me share with you the screen again. All right, so now I have some photographs to explain you. So now this is the reinforcement that you can see here. These are your fitments. This is your fitment, just the reinforcement. And in our case, it's given R10 fitment. R is again the ductility class, and 10 millimeter is your diameter for the reinforcement. Again, you can see this is the main reinforcement, longitudinal reinforcement or tensile reinforcement, and these are your fitments. So this is all good now. These are all the questions that we're going to solve along the way, but the ultimate goal is to find this moment capacity. Now let's to solve these problems. Let me list the general philosophy. What we really needed. So what we really needed, that for any problems, we will have a strain. We will find the strain. Australian standard will give us the strain. Once you know the strain, you will calculate the stress. How do you going to calculate the strain? Because you know the stress strain curve of the concrete and steel. Let's say this is concrete and this is stress strain curve of the concrete. If you know the strain from the standard, which is here, then you can calculate this stress in the concrete. Similarly for steel, we generally yielded, so you can have a yield strain. So you can take the FSY, which is generally 500 megapascal for steel. So for steel is easy, but for concretes we can calculate that. So once you know the stress, you can calculate the force in the steel and concrete, in the steel force and concrete force. How do we do it? Just multiply by the area. Multiply by area to the stress, that will give you the force. Once you know the force, you can calculate the moment. Right? Moment is equal to whatever the force times by lever arm or Z, perpendicular distance. So that's the overall philosophy, that we got the strain, then we got the stress, then we got the force, and then we're going to get the moment. Right? So I hope it is makes sense, the philosophy. So let me get this one here. Let me get this this guy here and put it here, nice and easy. Okay, very good. Now in here we will have let me put the another two, that's the fitments. So these are your fitments, and just leave it this one. Okay, so let's say this is the fitment. So now you have a tensile reinforcement 3 and 24, right? It's given in our examples. And we have hanger bars, because look at this, these are hanger bars. Okay, because if you look at our figure, you can see these are hanger bars here. These are hanger bars, right? To hold your fitments in the position. So they are there not in the design purpose, just for to hold this fitment. So these are hanger bars. Main criteria is this 3 and 24 bar. So we have this one. Let's give them small b is 300 millimeters, given in our examples. I can show it to you. 300 millimeters B. Capital D is 600 millimeters. So capital D is 600 millimeters. Capital D equal to, right? All good. Now cover is given to us. 14 millimeters cover. Where is given? I can show it to you here. 14 millimeter cover is given to us. Now always we not going to use capital D in our design. All the designs that you're going to see, we never going to use the capital D. What we generally going to use is this effective depth, and that is small d. Now effective depth, how do we calculate? Effective depth small d equal to this capital D, which is 600 millimeters, take away this cover 40 millimeters, take away this fitment diameter 10 millimeters, take away 24 millimeter divided by 2, because you can see this is in the middle from this. So in that case, if you use the calculators, you would get these dimensions as a 538 millimeters. So that's the effective depth that we're going to use it in our example all the time. Now then, as I mentioned, what philosophy we're going to follow? We're going to get the strain, then we're going to get the stress, then we're going to get the force, and then we're going to get the moment. So let's get the strain first. Let me draw up these nice diagrams. Okay, how about let's get this
line, reference line for us. And if I want to draw, probably we need to, as I mentioned, we just generally going to draw it everything from this D. So let's draw the vertical line and stress in the concrete. The stress in the concrete, the maximum stress in the concrete is 0.03. Where it's given, I can show it to you here. If you look in the beam this week and next week for the bending, we are just dealing with the 2 page only. This page number 110 here. Good news is that next page is 111. That's it. Week 3 and week 4, nothing else, just a 2 page. Probably we will use some of the tables back and forth, but these are the main two page that we're going to focus all the time. Now someone might say that maximum strain in the extreme compression fiber is taken as 0.03. If it is too small for you to read, I encourage you to open your own standards, go on page number 110 and go to the clause 8.1.3 to have a 0.003. This exercise that I'm showing you here, some students might comment me and question me, oh, it's too small to see on the screen. I agree with you. That is too small to see on the screen. Therefore, I encourage you to open your own standards, go to this line, have a feel about where there's living and get that value. But this is just the directions. You can walk. I will give you the directions, but you need to follow the direction by using your own standard. So 0.003 that is given. As I mentioned, standard will tell us the strain for this. Let's say the strain in the steel is AST. We don't know. Let's say standard does not give, we will calculate that. So that is a strain. The first thing is done. First thing is done, meaning we have done this. In case if I lose the connections, this surface flow is getting warm. If I lose you, just stay there. I may reconnect you with another one. So in case something is disconnected technically, just stay there on the Teams and I get back to you in 5 minutes. I'm just giving you a heads up. So this one is a neutral axis, TM, depth of the neutral axis, that will divide your concrete beam into 2 zones. Above the neutral axis is compression zone, below the neutral axis is a tension zone. So that is the depth of the neutral axis and that is denoted by dN. Let me put neutral axis here and a neutral axis. After strain, as I mentioned, we're going to get the stress. Now, how do we gonna get the stress? Let me draw the line, first one, and from that stress, we will have this Vitali stress block. That is the stress in the concrete. Someone might say, why you not draw up to the neutral axis? I agree with you. We'll get back to you with that one. The maximum stress you're going to get is alpha to FC dash. Right? So that's alpha to FC dash. That's you're going to get it from here. Alpha 2, that's the equations for that, and FC dash, that's a concrete compressive strength, that's the stress. And this depth will be given by the factor gamma dN. Now someone said, oh, stop here. What's happening here? Because your typical diagram for concrete is look like this, right? Sigma C EC, and that's your FC dash. Once it's reach FC dash, and let's say then it will be cross concrete. So that is a typical one. But I did not draw this one. I did not draw this one, meaning that I did not draw like this diagram, that red one. You agree with me, because I should draw the red one because that's the typical stress strain curves that you see. Why I did not draw that that red one? Now, so for that reasons, why I did not draw, because you can see engineers have a difficulty to find the area under this curve if it is this non-linear curve. So what engineer come across saying that, all right, how about we replace this exactly the same this blue one by this rectangle. So area under, let's say this is area under the curve, and this is also area under the curve. Let's say 1 and 2, they are same. So you find in a way that this area, the height of that one would be alpha 2 FC dash, and the width of this one would be gamma dn. So you can look at these two lines on the left side. You have this blue color one. That's engineers not able to find the area under this curve. But if someone asks you to find the area of this rectangle, you can easily find that, right? But they are approximately equal. So standards makes our life easy by saying that, hey, this is our actual curve. This is our real curve. This is our real stress strain curves. Real stress strain curve of concrete, right? So you can represent that equivalent stress strain curve by this block, right? So if I show it to you, this guy, Vitali stress block, 1937, he proposed this idea of in 1930, and we still use it. Okay, standards still use it. So therefore, we just write this in that fashion that if you have a 0.03 strain, you will have alpha 2 abscess stress, and that is the depth of, and we can't go up to here. Okay, and for steels, we can just have a tensile force in the tensile stress in the steel. Let's say sigma st. That's the stress in your steel. We don't know that what is the stress in the steel and alphas. So I hope you're following. We done stress to stress, and now we are going for the force. Now for the force, so here is a strain, here is a stress. Now we are going for force. So if I want to calculate the force in the concrete, I would have a force in the middle acting in the center of the rectangle, and the center of the rectangle, the overall height is lambda dn, then the center of the height would be lambda dn divided by 2. So this is, let's say, concrete force C going in this directions, and the distance from the top would be, location of that force would be gamma dn divided by 2. You with me, right? And this tension force in the steel will go opposite, and that would be T, right? And the distance between these two would be Z, which is a lever arm. Right? I hope you understand everything. The strain, stress to force, and finally the moment, AMUO, that would be, let's say, T times Z or C times Z, like force times lever arm. So I hope you understand the transition, cross section to the strain, to stress, to force, to moments. Okay, that's the general philosophy that we want to follow, like strain to stress, stress to force, force to moments. Okay, so I hope it is clear to you now. Now our ultimate challenge is to find the neutral axis depth. This one. Once you find the neutral axis depths, our most of the work is completed. So how do we going to find the neutral axis depths? Now from the force equilibrium, I know that some of the force, that C, which is the green one here, that is going left to right, and the red one going right to left. So this force should be equal and opposite to have an equilibrium. Otherwise, if this C force is more than the T force, then your beam is rotating. When you build the beam and put it in the buildings, it should not rotate, right? It should be equilibrium, internally equilibrium, by saying that all the force going to the compression should be equal to the force in tension. You agree with me that this beam is in equilibrium, is not rotating. So for that case, we know that C equal to T. So that will help us to unpack this dn. So let's say you want to find, so let's say you want to determine neutral axis depth dn. How do we find that? Concrete force equal to tension force, right? So concrete force, let's denote it by C, tension force as a T. Now let's then find the concrete force. Concrete force C. Now as I mentioned, force equal to stress times area. Concrete force stress of the concrete F alpha to FC dash. Someone may say where it is coming from. We discussed that concrete will experience alpha to FC dash. Someone might say, why not FC dash? Because your concrete has a capacity of FC dash. Why do you multiply by alpha 2? As I mentioned, we need to multiply by alpha 2 because the examples give you FC dash. That's what your maximum concrete compressive strength. But standard does not allow you to take alpha 2 FC dash. Instead of 25, it will reduce by alpha 2 because of this equivalent stress block. So this is your stress. You with me so far? Now the area. Now for area, I need to explain you in these figures. Look, this is the figures that I think this is the, we're going to do this test, beam test. So for examples in here, if I draw this one in the red and just make it a little bit bigger, this one. Yeah, so now you can see that one. So you have seen this is how much? I think 300 by 600, I believe. Yep, 300 by 600. 300 by 600, right? That is the overall. Somewhere is a neutral axis where you need to have a dn value. Now area. So you remember this is the cross sections that we done. This one here, green one. Let's say this one. This is the gamma dn. You can see this green one, gamma dn. So you with me that this is gamma dn. You with me? This is gamma dn. So if I want to know the concrete area, then this area would be gamma dn times by this b. Do you with me? Right? This cross section area, that height times width. So gamma dnb. This is the area that top concrete compression would be experiencing when is carrying the compression force. You with me, right? So for that case, we have area is gamma dnp. You with me, right? Now we have some value to this is constant, by the way, alpha 2. I will show you where it is located. Alpha 2 is close 8.1.3 and alpha 2 is given here. 0.85, take away 0.015, FCD, make sure it's greater than 0.67. If it comes less than 0.67, we take it as a 0.67. So I'm copying that one. 0.85, take away 0.0015, FCD, make sure alpha 2 is greater than 0.67. So 0.85, take away 0.015, FC dash is 25 given in our examples. Here is given in our example, FC dash is equal to 25. So that is 25. Let's use the calculators. 0.85 take away 0.0015 times 25. You get 0.8125, which is greater than 0.67, so that is okay. 0.8125, which is greater than 0.67, therefore it is okay. Now we can get this gamma as well. Just on the same standard 0.97, 0.025 FC dash, by the way, is on page number 120, section 8, close 8.1.3, equation number 8.1.32. We can copy this equation again. Gamma 0.97 take away 0.025 FC dash, make sure gamma is greater than 0.67. 0.97, 0.025, FC dash is 25 megapascals. So it you in the examples that FC dash is given 25 megapascals. And if I use the calculators, 0.97, 0.97, take away 0.025 times by 25, you get 0.9075 greater than this value, so should be okay. Zero point 0.9075, which is greater than 0.65, therefore is okay. So let's get back this one here. C is equal to alpha to FC dash, stress, force is equal to stress time area, gamma dN times B. Alpha to 0.8125, we just calculated. FC dash 25, given in our examples. I can show it to you again. Then FC dash is given here, 25 megapascals. And then gamma, we just calculated 9075. dN we need to find. B is given in our examples. This one 300 millimeters. So let's plug that value. 300. So if I use the calculator, (0.8125) times by 25 times by 0.9075 times by 300, you get 5530.08 dN. 5530.08 dN. So let's give them equation number 1. So that's this concrete force we calculated. Now let's calculate a tension force in the steel. Tension force in steel, let's say T. Now we need to make a big assumptions here. Big assumptions, let's put it in the red. Assumptions. What is the assumptions? We're going to make a check on these assumptions that steel is yielded. That's the assumptions that we want to make it right now. And then we're going to check later whether it's gonna yield it or not. If it is not yielded, then these calculations would not be valid. Now what does it mean the steel is yielded? For examples, let's say this is a steel stress strain curves. The standards allow you to use these elastic, perfectly plastic stress strain curves. So this is the yield point, ESY and FSY. So we say that when we load the beam, the steel will going to be yielded. Yielded meaning it will permanently deform. When you unload that, the steel will not gonna come back to its original positions. Now the philosophy here saying this, in reinforced concrete design, we want to yield the steel first. This is what standards wants you to do, because that will allow to have enough ductility. So we must, so if someone asks you, you have a reinforced concrete beam, you have a steel and concrete, who fail first? Is it the steel going to fail first or concrete going to fail first? So your answer is yes, the steel will going to fail first. That's what we want to do, because otherwise, let's say in this beam here, let's say you have this steel, right? Let's say you have this steel bar. These are your 3 steel bars sitting here. Now if I load this beam, if the concrete cross, let's say concrete cross first. So if the concrete start crossing before the steel yielded, then if I am sitting here under your beam, all concrete will put on my head and your steel bar is sitting there doing nothing. So we make sure that the steel will yield first, steel will going to bend, and so that hold the concrete. The concrete will not just brittly snap. So we make sure that steel bend, yielded, and then the concrete will start crossing. This is the sequence, the failure sequence we want to design in a way that we force the steels to yield before concrete start crossing. So therefore we make these assumptions, we making sure that when we apply the loads, we make sure that steel is yielded. Okay, we make these assumptions and we're going to make the check later. So if the steel is yielded, then the force is equal to stress times area, same equation by the way. So force in the steel is represented by T. Stress in the steel, we make an assumptions, right? Then the steel will yield it. So we will take FSY and the area of the steel AST. We will calculate each one of them one by one. Now FSY is 500 megapascals and bars. I can show it to you here. Probably if you go to the section number 3 somewhere. Section number 3 somewhere they mention 500 megapascal. Yeah, so ductility, class and ductility, they have a yield strength of 500 megapascal. Look at the class L ductility, you have 500 megapascals in table 3.2.1. So we use 500 megapascals. Now how much AST, how many bars we have given? We have given 3 and 24 bars. Now area of steels, we have 3 and 24 bars. We use the Rio data tables. Let me grab the Rio data tables somewhere. Yep, here you go. So we have these Rio data tables. In these Rio data tables, if you go to the page number 16, again, if you can't read it, I encourage you to open your own Rio data tables. We have 3 bars and we have 24. So number of bars, you have 3 go across and 24. So you have a area of 1356 millimeter square. I can lift it up here. So 3 bars go across, 24 millimeter dia, 1356 is the area of your reinforcement. So 1356 millimeter square. By the way, this is Newton per millimeter square. Megapascal is. So in this case, if I use the calculator, 500 times 1356, you get 670. You get 67800 Newton. Right? Now this AST is 1356 millimeter square. Now we can go back to these equations where you have equilibrium and we plug the values. Now here, force equilibrium, C equal to T. Let's plug the value. C is 530.08 Tn. And then you will have T. Tension force is 678.00 newtons. So Dn equal to 678.00 5530.08. divided by 5530.08. You get 122.6 millimeters Dn. Once you find the Dn, your most of the let me put a 60 millimeters. Most of the work is completed. Most of the work meaning completed means then you can go back to this diagram again and start calculating. This Dn now is 122.6 millimeters. Now we can calculate this strain because this strain is known to us, but this strain is not known to us. So we can calculate the strain in the steel. Let's calculate the strain in the steel. Tensile strain in the steel. Let's put EST. If I draw the diagram, the same diagram that you have up, 0.03. This is DN 122.60 millimeter. By the way, I just copy this diagram that I explained you before. This diagram here, this strain diagram, I copy that one. You have EST. Now this whole thing is 538 millimeters. Where this coming from? You remember that we calculate the effective depth. This one here, 538. This one here, this red one, 538 millimeters. So that's I put it there. So if I want to calculate this value here, then it would be 538 millimeter. Take away this 122.60. 538 take away 122.6 give you 415.4. 415.4 millimeters. So now we can use similar triangle. What is similar triangles? That this horizontal distance. Why similar triangle? Because this angle and this angle are same. Therefore, we can use the similar triangle. 0.03 horizontal for these first triangles. Horizontal distance of first triangle to the vertical distance of the first triangles equal to, let's say this is second, horizontal distance of the second triangle over the vertical distance from here to here. We calculated for, oops, yeah, as I mentioned, see sometimes, yep, it's turning it on. Hopefully it will comes in the right shape. Yep, that's good. Thank you. Getting back 454 millimeters. Right. So if I want to simplify, EST equal to 0.03 times 450.4 millimeter over 122.6 millimeters. So if I just use the calculator, 0.003 times 450.4 divided by 122.6. So 0.01 strain. So 0.01 is a strain in the steels. Now you remember that we made these assumptions that steel is yielded. So we can calculate this yield strain and we will check whether steel is yielded or not. Now we need to calculate the yield strain of steels. The formula for strain equal to Young's modulus. I think the stress over Young modulus. Stress in the steel over Young modulus or elastic modulus. So the stress we get 500 megapascals. You know, I show you that one, right? And the Young modulus is 200,000 megapascals. I can show it to you again. That in the section number 3, modulus of elasticity 200,000 for steel, yield strength of the steel 500 megapascals. That's I will substitute. So the yield strain, this is by the way yield strain, this is yield stress and Young modulus. So if I use the calculators, 500 divided by 200,000, you get 0.0025 as a strain. So yield strain is equal to 0.0025. So check for yielding. Since the steel strain is 0.01 is greater than yield strain, the Rio steel are yielded, right? So our assumptions are valid now. If it is not yielded, we are in trouble. We are in trouble meaning we can't use FSY. We will have an examples. So by the way, this is the typical stress strain curves. This is 0.025 yield strain we calculated. This is FSY 500 megapascals, and we are somewhere here, very far. So 0.01, which is good. This is the actual strain. So we can use this one. So if it is not yielded, then we need to calculate the stress here and then use that cell. We can't use 500 megapascals, but it's yielded, which is the good news. And that's what we wanted. If it is not yielded, standard will not going to like it. It will give you the heavy penalty. Heavy penalty meaning it will not allow you to use the capacity that you wanted. It give you the very severe penalty on your design. I will tell you where the penalty coming from. We have an examples where we will receive the penalty from the standard by some reduction factors. So I will tell you that one in a reducer. So I think the yielding is done. Then in that case we can calculate the bending capacity. MUO. Now the bending capacity MUO would be C times lever arm Z or T times lever arm Z. I think T we already calculated somewhere. So we can use that one. Yep, here you go, 67800 Newton. So we can use these equations rather than another one. T times Z, which is 67800 Newtons. Now the Z lever arm. Now Z lever arm is here. If you want to calculate the Z lever arm, you would get this D, the whole total D, and we know this D is 538. Take away this gamma D and divide by 2, so that will give you Z, right? Lever arm Z. So let's write it here. Lever arm Z equal to small d gamma dn divided by 2. Small d 538 millimeters. Right? We calculated that one before. I can show it to you. Here you go, 538. Take away gamma. Gamma we calculated. Where it is? Oh, here you go, 0.9075. 0.9075. Take away dn, we calculated. dn is 122.6. 122.6 over 2. So let's use the calculator. We have 538, take away 0.9075 times by 122.6 divided by 2. You get 482.37. 482.37 millimeter. That is a lever arm. 482.37 millimeters. So let's use the calculator. Times by 678. Tension force is how much? I think 678. Right? Yep, 678. Times by 678,000. So you get this big number, 327. 047 029.5 Newton millimeter. Generally we like to have it into the kilonewtons millimeters. So that's, again, you can just divide by 1000, divide by 1000. So 327 kilonewton meter. So that is your answers. If you want to do the reduction factors, I will show you the reduction factors with 5 mu. So this is a capacity reduction factor, by the way. And these capacity reduction factors here, bending without the tension and compressions for member with class and reinforcement, table 2.2.2. We're going to use 0.85, by the way, because our steel is yielded. I will show you another figures that I have in my another standards. The same standards, by the way, but I have a notes there. Page number 36. Look at this diagram here. Compression control, transition, and tension control. We have tension control, by the way. So we are using 0.85. By the way, tension control means how much steel put in the beam, right? So 0.85, when the steel is yielded, you can have 0.85. If steel is not yielded, the standard will provide penalty up to 0.65. So we are reducing only 15% because saying that our steel is yielded. So therefore I am taking 0.85. Okay, if you are not here, we will take you through these diagrams later on these ones. So the capacity factors account for uncertainty in the material strength. Why do we reduce it? Just 15%, because the concrete is very complex materials. It will not, if there are two persons making the concrete, they will not get the same strength, right? So inaccuracy in design equations, we might screw up some rounding errors and all, and approximates in analysis, some assumptions, variation in dimension and variation in placement of reinforcement. So there are some uncertainty that the standards wants you to take into account. Therefore we have therefore we have this 15% penalty that goes into our design. 0.85, by the way, times by 327 kilonewton meters. 15% not bad. 327 times by 0.85, you get 278. You get 278 kilonewton meters. There are a couple of checks that we generally make it in all the examples. We have 9 minutes, so let me do the couple of checks. There is a ductility checks that Ku should be greater than 0.36, right? So that's we need to making sure that Ku would be greater than 0.36. So Ku, this is called ductility check, is equal to dN on D. So depth of the neutral axis was 122.6 over D. D we calculated how much D we calculated, somewhere here, 538. So 538, 122.6 over 538, you get 0.23, which is greater than 0.36. Therefore ductility check, it is adequate. We make the standard happy. There is another one that minimum, you need to make one of these checks as well. If you come across in any beam examples, you need to do the either minimum check to making sure that you provide adequate to concrete, or you need to make sure you have minimum steel reinforcement requirements, so to prevent the sudden failure. Some engineers are playing very smart in terms of saying that they might saying that, all right, I don't want to put any steels, my concrete is good enough. Then these guys are playing smart bags, saying that you must put the minimum reinforcement. So regardless of your design standard, saying that you need to put this minimum minimum reinforcement. So AST minimum, I think, by the way, this one coming from here on clause 8.1.6 point. Alpha B is 0.2 for rectangular sections. So we put alpha B 0.2. Capital D 600. We have capital D 600 given in our examples. Capital D 600, and the small d we calculated. Small d we calculated 538, I believe. We done it many times, but 538 square. FCT dot F. Now to calculate the FCT dot F, we can go back to the section 3. fct.f, which is equal to 0.6 fc dash, is in clause 3.1.13, page number 45, is just the tensile strength 0.6 fc dash. fct.f equal to 0.6 fc dash, 0.6 times square root 25. fc dash given in our example, so it's a 3 megapascals. So it's 3 over fsy 500, this is megapascals, times by bw is your read, small d is 538. Let me show you one by one. 500 we done, bw 300 is given in our examples. This is 300, and what else? And D 538 millimeters. I think I show you that one as well. So if you just use your calculator, you will get 241 millimeters square. Our AST is how much? Our AST was 1356 millimeters. So AST 13560 millimeters square is greater than AST minimum. Therefore, we have 241 millimeter. Therefore, it is okay, right? So let's finish this one here. Probably there is a one more check, but that's I will demonstrate in one of other examples. That's this check. The minimum one is just 1.2G FC2 dash, and Z is your BD square over 6. So that I will show it to you later. Because of the time constraint, we're not able to show you. But I will be here. Any questions, any comments, or anything that does not make sense, too fast, too slow, is completely not making sense. Where this value coming from? These standards I can't download, I can't print anything. Anything that is puzzling you, that anything is stopping you to learn this reinforced concrete design, like anything that can stop me saying, this is the things that I stop me. No, all good. It seems that everything is going on the spot. Thank you, Haider, for taking the theory. We all see you in the workshops to have more fun.